Good morning, everyone. So we are glad to have you all here today for our second day of our workshop. So we will start now our participant presentation session, and during this session we have two moderators, so my colleague, Dr. Emira Kibir, and myself, to present the first presenter, which is Ghada Mahjoub. She will present, the title of the presentation is Drug Repurposing, a Signature-Based Approach to Accelerating Therapeutic Discovery. So, Ghada, the floor is yours.
Thank you. So welcome back, everyone. I hope that you enjoyed the workshop. So my name is Ghada Mahjoub, and I'm pleased today to present to you my master project work titled Drug Repurposing, a Signature-Based Approach for Accelerating Therapeutic Discovery. So this work presents my academic journey as a master student in bioinformatics file, and it was supervised by Dr. Qais Dira. First of all, I will go through a quick review on the traditional drug development process, where drug discovery and development, especially when we are talking about cancer therapy, is a long and high cost process, which take an average from 10 to 17 or even 20 years. And it includes several steps like discovery, design, preclinical, clinical testing, and regulatory approval for to be then posted in the market. So this underscore the need for a faster and more cost-effective solution. Here we are representing our proposed solution, which is the drug repurposing, a promising strategy for addressing these challenges. So drug repurposing in its most basic level is linked to recycling drugs, where we are identifying new uses for existing drug, known for their safety effects to speed up the process of making new treatments. I have to mention that we can say drug repurposing or reprofiling or also retasking. And to more understand this approach, I will go through its historical evolution. So it began with an accidental discovery, like using medication for angina. Then by 2004, it shifted to become officially systematic and research-driven strategy. And here we can mention some notable examples, like aspirin, which is a drug transitioned from pain relief to prevention of cardiac events, or minoxidil, which is a drug transitioned from hypertensive to a treatment for hair loss. Also, and by 2007, oncology expert highlight successful example of repurposed drugs in cancer therapy, and this marked a milestone in oncology domain, where we have some repurposed drug used in cancer therapy. And also, I have to mention that this approach gained more attraction during crises like COVID-19 pandemic, which emphasized the urgent need for faster drug development driven by computational bioinformatics tools. So drug repurposing uses several approaches, and here we are targeting the signature-based approach. So it is the method that identifies new therapeutic use for existing drugs by comparing their molecular signature. Here we are talking mostly about transcriptomic data with disease signature, and it examines the overall interaction between drugs and disease, where we are looking for similarities in their molecular profiles to find potential matches. And this approach helps uncover drugs that may counteract disease effect by reversing specific gene expression patterns. At this level, our objectives are to develop an automated drug repurposing pipeline, then integrate large-scale data from links or CMAP dataset to establish matches with cancer genetic signature, and finally to create an interface that facilitates the identification of potential drug candidates. And to achieve all these objectives, we are working with an environment that leverages advanced computational tools like the use of R programming language and and Linux Ubuntu as an operated system. And also, this project required two main types of data. One which represent the disease extracted from geodatabase, and the other for the drug perturbation dataset like links or CMAP dataset. In general, our approach begins with identifying molecular signature, where we are analyzing cancer-specific gene expression for our targeted disease, then begin to develop an automated pipeline by integrating links or CMAP dataset for drug perturbation databases. And once we have signature for drug, also for disease are prepared, we can move on to the calculation of our connectivity score, which is a measure for drug-disease signature relationship. And once our pipeline is done, we can move on to create an interactive user interface where we are building a platform that integrates all this pipeline. Focusing now on the pipeline itself, it begins with the gene expression data as an input and ends with the selected drug candidates as output. It goes through several steps. So first of all, we have the data acquisition step, where we are downloading gene expression data using the GeoQuery package. Then we move on to the control quality of this downloaded data set using the Lemma package. Moving on, we have the differential expression analysis to identify key gene changes, and then we can annotate our significant genes using different libraries. And here we are targeting significant genes for our disease. Like this, our signature for the disease are prepared, and we can move on to the preparation of drug signature by analyzing drug perturbation dataset, where we are comparing with some drug profiles using several packages like PharmacoGX and Experiment Hub. And once we are done with this step, we have now our signature for drug and signature for disease that are prepared, and we can move on to the calculation of our connectivity score by ranking drugs by their efficacy and their scores based on FGSA methods. And our final step is the selection of drug candidates and their visualization, where we are illustrating the top drug candidates using Panda package. Here I will show you some results of an example of studied disease, which is lung cancer disease. So first of all, we've extracted the gene expression data for lung cancer disease using the accession number from Geo database. And then we have extracted the most significant genes and annotated them. So how we had found the differentially expressed gene by log fold change values that indicate the gene expression variation, and here we can notice the negative values that suggest lower expression in cancer samples compared to normal tissues. And like this analysis highlights specific genetic deregulation in lung cancer. Now we can move on to the integration of our link dataset and apply gene signature from drug perturbation database to identify potential drug candidates for repurposing in the cancer context. And like this analysis investigates how various drugs affect the expression of genes significantly linked to our study pathology. And here I am showing you the lung cancer as an example. So first of all, in our pipeline, we had optimized and validate the pipeline using a smaller dataset for drug perturbation dataset using the CMAP small dataset, which is an extension from CMAP database that is used usually for testing and validating pipelines. Then we move on to replace this database with the links dataset to expand the analysis of drug effects. And here I have to mention that different gene annotation methods was used to align with links signature. And like this, we repeated all the process using the same database for a disease, which is the lung database, and extract their significant genes. And like this, we had identified intersection that generated more than 1,721 common genes. Now, since we are sure that there is intersection between gene signature linked to lung cancer and links data set for drug perturbation, we can move on to the calculation of connectivity score. But first of all, what is connectivity score is? So it measures the association strength between significant gene signature and drug-induced perturbation, and it is a crucial method that assign drug perturbation, drug repurposing potential. And here we can ask how from this connectivity score we can say that this drug is used for repurposing or not. So we have two types of scores. First of all, we can have high positive score, which indicate that the drug may not be suitable for repurposing as it mimics the disease expression. Or we can have a negative score that suggests that the drug could reverse cancer-associated gene expression, making it a potential drug repurposing candidate. Here we have our results that illustrate mostly the top 10 drugs that show the lowest connectivity score, which indicate that their potential to reverse genetic disruption. And if we want to zoom in our analysis, here we have the 5 most drugs that show the most negative connectivity score and also high significant statistical score, making them a promising candidate for repurposing. So here we have, for example, BRG, THZ, and pazopanib are the most promising candidates showing negative connectivity score with strong statistical significance for further exploration. Also, we have to note that the other drugs that we had identified, like ivodiamine and phenotyrol, although that they are lesser known drugs, but with their significant scores, they need further research. And at this level, we can ask ourselves how to prioritize our research and choose which drug we should prioritize. So in our case, we noticed that pazopanib, not with its results and showing a very high statistical result and negative connectivity score, but also as an approved oncology drug for kidney cancer, which validate more our approach. So this drug can be the first one to prioritize for further exploration. Now, since I have explained the pipeline and validate that we have a list of drugs, we can move on to the creation of our interface, where we are building a platform that combine all this pipeline into a layered architecture interface. So basically we have three layers. First of all, we have the data layer, which contain the databases for the disease and the drug. Second, we have the service layer. This is actually contain all our scripts for the pipeline and also the Shiny service part for our interface. And finally, we have the application layer, which is the layer that actually the user is interacting with to upload his own data and then visualize his results. So we called our interface redrag, which is designed to simplify the complex drag repurposing process. For the moment, we are targeting oncology domain, and it allows user to easily upload dataset, perform bioinformatics analysis, and explore results through an interactive platform. Here we have a screenshot of our redrag interface. So we have a section where the user can upload his data set for the disease from a local CSV file or just to enter an accession number from a geodatabase. And like this, the links data set is automatically uploaded from our server, and the process of analyzing start. And like this, we can finally visualize our results as a list of top drag that can be repurposed. Now, since I've showed you the redrag interface and also explained the pipeline, let me summarize all this. So our project streamlines drag repurposing with an automated pipeline, which is designed to identify drugs that can counteract cancer-specific gene signature. And by using links or CMAP database, it uses connectivity scores to pinpoint drugs that reverse harmful gene expression changes. And also we have to note that OK highlight is the development of an R-Shiny interface, enabling intuitive data processing and interactive result visualization, which make bioinformatics analysis more accessible and efficient while saving valuable time for larger scale studies. Also, we have planned some next step to enhance further research, like expanding our database sources to provide more ownership analysis, improve data visualization tool to allow more interactive and intuitive and result interpretation. Also, we are planning to integrate some models of machine learning and deep learning to deepen our analysis of gene-drug interaction and enhance predictive accuracy. Also, we are planning for some validation steps, which include in silico checks and collaborative partnership for in vitro or in vivo experimental verification. Thank you all for your listening, and I want to thank also my supervisor, Dr. Qais, my guidance, Dr. Osama, and my twin, Rihab Mahjoub. Thank you.
Thanks, Nadia. Presentation.
Thanks, Heather. Very nice presentation.
Yes.
Okay. So I have a small question regarding the databases of the drug databases that you have used. So you mentioned here links
Yes.
and CMAP,
Yes.
but your analysis was based on links only.
I'm showing here links only, but I used both of them.
You use both.
Yes.
Okay. So the second question is, in these databases,
Yes.
you have also perturbation data,
Yes.
which means the transcriptomic signature
Yes.
of, basically the connectivity map was done not based on drugs, but also based on knocking out or knocking down some genes, and
Yes.
then we measure the transcriptomic changes based on that. Have you excluded those perturbation data or in the separate?
Yes, thank you for your asking. So for links data set, we have signatures that are prepared and ready to direct use for connectivity score calculation. But if we are using CMAP dataset, we have to go through several steps to identify these signatures. So we have to investigate all these genes and annotate them and extract most significant genes and investigate also if there is intersection between them. And like this, we have a signature for these drugs that are prepared to be used in the calculation.
So you did this pre-processing on CMAP data before using it?
Yes,
Yeah,
yes.
Okay, one last question regarding the links. Links
Yes.
provides only 1,000 genes. Those are the cancer kind of genes, right?
No.
And for everything.
No, it has more than 50,000 genes, but this intersection, just the intersection between the lung cancer database that we are targeting and the links database. So it is the intersection between them before the step of calculation.
50,000 genes.
Yes.
Are you sure?
Yes.
So the connectivity map is mainly having the whole transcriptomic profiles, but
No,
links-
connectivity map is a method for calculation. Links dataset contains the genes or let's say the signature that are prepared for this calculation. And the intersection between the two datasets allow us to pass to the other step, which is the calculation of the connectivity score. But if you are talking about the links database itself, it contains a very long list of genes that can be used for other maybe disease or cancer types.
But is it specific for cancer or?
No, for very yes.
Thanks.
Thank you.
More questions?
very much for
Thank
this presentation as well. If you would, because you highlighted in the future work that you are intending to incorporate drug gene interaction or a drug interaction, so what would be your approach?
Basically, we are going to integrate machine learning or deep learning model to do this part of work to analyze the drug interaction or drug disease interaction and found interaction. Before that, we go for the analysis of all significant genes that we have identified and go through the connectivity score calculation.
So to be integrated before the score.
Yes, yes, yes.
I have a very simple question.
Yes.
You have already completed an interface, so you collect the data from a database on the internet, right? And you do processing and then you show the results.
So our interface, not for the disease you are talking, database for the
Take
disease.
two slides for this slide.
This one? Yes. So the user can upload his own data set for the disease from CSV file, local CSV file, or just to enter an accession number to upload it directly from the geo database.
So yeah, your interface is connected with the database.
Yes,
right?
yes.
And the processing is done on your machine.
Yes.
And then it shows the results.
Yes,
Okay, and it works.
it works, yes.
So, yeah. For the moment, we just, as a result, we just display the table with the top five,
Most.
let's say,
Yes.
most significant. But what we want to do is to go through any kind of visualization like network interaction or something like this. That's why we need to integrate many things. And maybe here we are based only on signal-based approach, so we need to investigate other type of approach for the repurposing and combine everything that created in the same plan.
And in future, you wanted to support your program or interface with machine learning or deep learning
Yes.
engine, I would say, to display the results, to analyze the
Yes.
data and display the results. And do you have enough data for that to train or to customize deep learning model?
Yes, since we are using open access databases, so we can do this. Maybe we can go through combining some the same type of cancer or like this. But for drug perturbation dataset, yes, we have other type of, for example, links database that can have a million genes that could be analyzed, integrated. Just we have to put in mind to have not done in local PC, but yes.
Very interesting. We'll see.
We have one question. So let's assume that you have a lung cancer data set and you upload it here and then you've got a list of drugs.
Yes.
Then Muhammad, you do another data set for both of the lung cancer and then because it has a different signature. Okay? You've got also different drugs.
Yes.
So which one will you trust and why if you have this difference?
So.
The same disease.
So for the two cases, we have a list of drug that could be repurposed. First of all, we should go through a literature research and education to see if these drugs are already used in oncology domain in general. Then we have to plan for some elimination for some of these drugs. And also we have to go through validation step like using molecular docking or structural bioinformatics to more confirm these drugs before going for experimental steps to identify the really drug to be repurposed for this disease. But for the moment, we can go through the filtering of the two list of drugs. Then we can decide which one is more suitable for this lung cancer disease.
And Planet is a database called Prism. It's developed by Golden Institute. It has provided more than 1 million drugs, 1 million cell lines, including cancer cell lines, neurodegenerative disease,
Interesting.
everything.
Yes.
So it will be really to incorporate this also in the future.
Yes.
1 million times 1 million. So imagine how big this is.
Yes. Very interesting.
It's much more wider and
Bigger. Yes.
than
Yes.
these ones.
Yes. You have. Thank you for the suggestion.
Thank you very much for this presentation. I have one small question about this. So, you have to download the transcriptome data set. So I guess it's raw data, right?
Yes.
Raw data or processed
No processing data.
process. And so for the transcriptome, so
Yes.
So for the geo access also is the process data.
Yes, the process data, but we have some. So the second step after downloading is the processing step. Here we can here we can decide if this database could be used for directly integrated in our pipeline, or we need to go through let's say, steps to prepare them to be integrated in our pipeline.
But when you use the process data,
Yes.
so you have to run like the transcriptome RNA-seq analysis. So you have to get the genes, right?
Yes.
Then you have to integrate the links that are the
Yes.
and then run all that.
Yes.
I'm just gonna ask about the options when you run the decks. Are the options same options for any kind of data set that you're gonna use?
No, we have to investigate the type for the geo base. Basically, they are yes the same. But if we are using CSV file, we have to identify which parameter we have to work with and focus on, and then go through the other steps of the pipeline.
Right. Just for this, what we did, so you can download data CSV file,
Yes.
okay, which is text file. And what we are doing now, this step is to get the geo series matrix that we are extracting directly from the geo
database.
extraction amplitude and analyze them and automatically. So just put the GSC number and we call directly to data from gene expression amplitude, download the data and process all the data. Okay. So this is what we are doing now.
Any more questions?
Thank you.
Thank you. Thank you. Thank you. First, I want to thank for the invitation to this very interesting session. It's amazing to see that master students are able to present like this for this session. So the next presentation will be from Rihab Mahmoud from Pastor Institute of Tunis. She will give a talk around her work, which is about the application of the AI-driven bioinformatics for cancer research to study the interaction between protein and
Choose un perfinator. Reportage que você choose un perfinator. لا اللي تبدا غدا غدا سكرها يدي داخل. Good morning, everyone. So my name is Rihab Mahjoud, and I'm thrilled to be here today at the GARN event, where innovation and driver expertise converge. Today, I will take you on a journey into my master project titled Protein Ligand Interactions Analysis with AI-driven bioinformatics for cancer research. So to begin with, let me give you an introduction about solid cancer, such as those affecting the pancreas, breast, and liver, arise from tissues and are characterized by localized cell masses that disrupt organ functions. Their progression is driven by genetic mutations, signaling pathway disruption, and interactions within the tumor microenvironment. So protein ligand interactions, which involve the binding of small molecules to proteins, play a pivotal role in this mechanism and are therefore essential therapeutic targets. This brings us to the challenges faced in the treating of solid cancer. So the first challenge is the complex molecular mechanism. Tumor progression and resistance to treatment are driven by intricate molecular pathways, complicating therapeutic strategy. The second challenge is the limitation of current approaches. Traditional methods like in vitro, in vivo studies, and imaging techniques are resource-intensive, time-consuming, and not feasible for all proteins. So by that said, we can conclude that significance of molecular interactions, ligand-protein interactions are key in cancer cell signaling and proliferating, highlighting their importance as therapeutic targets. So there is a critical need for therapeutics that target ligand-protein interactions to enhance treatment efficacy, supported by scalable, user-friendly platforms that automate data processing and improve accessibility. Let me so give you the proposed solution that we suggest. We suggest an integrated platform which is development of an automated robust docking platform tailored to protein ligand interactions in solid cancer. So it combines molecular modeling, docking simulations, and AI algorithms and automates the process from data collection to docking analysis. This solution accelerates drug discovery, enhances reproducibility, and democratizes access to computational tools. So building on this proposed solution, let's dive into the details of our objectives. First, create a structural database for anti-cancer ligands. Second, automate ligand and protein preparation. Third, automate the molecular docking process. Fourth, facilitate result exploration by generating clear and concise tables. And finally, enhance reproducibility and efficiency by automating all the workflow steps. So to achieve these objectives, we propose the following methodology. The first step involves the preparation of oncoligand database. This phase focuses on curating, organizing, and preparing the database. So first, we extract the data collection, and for that we write on anticancerfound.org, and we search ligands specifically for pancreas, kidney, lung, liver, and breast cancer. The second step is identification of ligands. So from the information that we extract, we can extract the product name, year of production, Kimball link, drug bank link, and their indications. After that, we extract the SMILES from the Kimball database. And finally, we developed a function based on OpenBabel library to convert the SMILE format to PDB format and make it downloadable. Once all of these steps are done, we integrate the table prepared in a website called OncoLigand Database using Flask framework. Having outlined the preparation of our dataset OncoLigand database as part 1 of the methodology, let's move to the part 2, which is the automating of the molecular docking workflow. And the idea in general is to automate the entire workflow from ligand and protein preparation to perform molecular docking and integrate this process into a unified interface called DocSmart. So let me give you the general pipeline which form the backbone of this study, and in the next slides I will detail each steps. So firstly we initiate with the protein and ligand preparation that generate ligand and protein point PDB-QT files to perform docking simulation, and this will generate a result point PDB-QT file that will conduct the docking calculation to analyze these interactions. And after that, we integrate these steps into our interface DocSmart to enable research to conduct complex docking studies. So the first step is the protein preparation for the molecular docking. So to do this, we relied on protein point py script to download the PDB files from the RCSB PDB database using a request library, then convert it to a PDB-QT format using MD analysis library, clean this protein structure using PDB2PQR library, and remove water and molecular and add the missing hydrogen using also MD analysis library. By that, we optimize our protein conformation and enhance the docking efficiency. The second step is the ligand preparation for molecular docking. So we relied also for that on ligand point py script to retrieve ligands search and download them from Kimball using the Kimball API presented in the Python itself, and add the missing hydrogens using the RDKit library, optimize the geometry, and finally convert it to PDB-QT file using Mico library. By that, we have both protein and ligand are prepared format by PDB-QT file, and this makes the docking point py script perform the docking simulation using Vina library to generate as output pose docking point PDB-QT file, and also summarize key metrics including the binding affinity score and RMSD values. And after that, we can visualize all the structure generated from ligand to protein to their interactions using GMOL tools. All these steps are integrated into a unified interface called DocSmart. So this interface integrates our scripts developed protein point py, ligand point py, and docking point py. As input, we need the Kimball and the RCSB PDB identifier, and for the back end, we use Flask framework to develop, and For the front-end part, we use HTML and CSS for responsive design. Let me give you a closer look at the feature keys for this interface. So we have mainly a home page that include a welcome message and our logo, about us page that include the team information and our objectives, contact us page, the docking page that include the workflow down, and also the oncoligand database, the base anti-cancer ligand that we developed. After that, we extend our work by introducing a graphic neural network GNN pipeline aiming to enhance the prediction of protein-ligand interactions through advanced computational models. So we're collecting the data from the PDB bind database for protein-ligand interactions, then installing the requirement Python library for processing modeling and deep learning. After that, preparing the input data for the GNN model by converting it into a numerical and graph-based representation. Then define the architecture of the GNN for learning the interactions between protein and ligands. After that, training this GNN model using protein ligand pairs to learn interaction mechanisms, and finally using this trained GNN model to predict interactions and generate output file, which is the bucket point PDB and the interactions graph. Let's see and examine the result of this methodology. So first, we have the oncoligand database that provides a curated data set of anti-cancer ligands characterized by cancer types. This feature enhances the platform's practical utility by enhancing users to explore and select ligands relevant to their research. So the user access to the main interface of oncoligand database, and he can choose between solid cancer and liquid cancer. By choosing solid cancer, he can also choose between 5 types of solid cancer, and by choosing one of them, the user views the of the ligand information, including the name and their structure. After that, we have the result of the preparation of the proteins. So the script successfully automates the preparation of protein files for molecular docking by downloading the target proteins and convert them into PDB QT formats. So the following figures compares the original PDB file and the processed PDB QT file, highlighting the improvements and adjustments made during processing, such as removing the water molecules and structural cleaning to enhance docking compatibility. For the result of the preparation of ligands, the ligand point py script automates the ligand preparation for docking by retrieving ligand data from the Kimball database via its API and converting MOL2 files to PDB-QT format. So the results include a comparison of 2D visualization of ligands before and after pre-processing, highlighting the addition of hydrogen atoms, and also a 3D visualization of the processed ligands file, which is the PDB-QT file, demonstrates the enhancement structure after pre-processing. By that, we have the docking point py scripts performing the molecular docking between the PDB-QT file of proteins and ligands using the VINA algorithms integrated into Python. So for each docking simulation, we have 5 poses of docking were generated, and a table of affinity score and RMSD value evaluate the stability of the interactions. For our streamlined docking interface, DocSmart, which is a user-friendly interface designed to automate the molecular docking process from the file preparation to result visualization. And this is a screenshot of our homepage interface, which include all of the pages that we show. This is a short video of the interface. I don't know if it works. It didn't work, so. Unfortunately, for this part of the project, it is still in progress and require further work. However, let me provide you with an overview of the expected result. So the GNN model aims to generate interactions graph that present the relationship between the protein and ligand atoms. An expected outcome is the generation of binding pocket structure to identify the ligand's interactions region with the proteins. And as the picture shows, the interaction graph visually represents the molecular interactions with node as atoms and ages as predicted chemical interactions. By that, I finished the presentation. Let me give you the conclusion of the study. This study results in the development of an innovative molecular docking platform by addressing the limitation of traditional methods, often costly and complex. The platform offers an automated, user-friendly solution that streamlines and accelerates the docking process designed to analyze the protein-ligand interactions, particularly for solid cancer research. So it automates the file preparation for both proteins and ligands, perform efficient docking calculation, and visualize docking results interactively for the interpretation. Also, the integration of oncoligand database adds a practical value, facilitating access to relevant anti-cancer ligand. So, oncoligand database provides seamless access to curated dataset of anti-cancer ligand, enhancing the platform's practical utility, and the users can quickly find and test ligands relevant to specific cancer type. This work, of course, can have some improvement, especially in terms of visualization tool by upgrading to advanced tool for precise 3D visualization. Also, we need to improve the GNN model for better interaction prediction by addressing the channels like managing the large data set and capturing the biochemical complexity. Also, we can broaden the data set to include more ligands and protein data and incorporate multiple docking engines for versatile research needs. And before ending, I'd like to give a special thanks to all my supporters, especially Dr. Osama Khamesi, which is my supervisor, and Dr. Qais Qadira, and of course, special thanks to my twins, Ghada. Thank you. Thank you.
Thank you for the clear presentation and the good quality. Then I want to ask about why every time you remove the water molecule in the pre-processing, let's say, step, I want to know why you remove this.
Yes. So as Dr. Osama yesterday mentioned that we need, before the docking, to perform the docking, we need some preparation. And one of the steps, which is the elimination of water. Why? Because the water is not in the protein, but it is in the environment of this protein, which is not good. And the RCSB PDB give us the protein point PGB file, but this protein is done with the crystallography type, so it contains the water that need be to remove.
Thank you for the lovely presentation.
Thank you.
I would love to know why did you decide for the model, for the GNN model? Why did you take any other one? Is it because Python is providing it for free and it's easy to use? Or did you try other models and this one outperformed all models you tried?
So GNN, thank you for your question. GNN model is a deep learning type. We didn't finish this part, but why we choose it? Because we have a large data set, which is 1.7 gigabyte, and we can rely on to a deep learning model to perform and see if there is a more accuracy between, if we do an interaction between a ligand and a protein by converting them to imagine. So it will show us some points and they will be connected. And after that, we have the calculation of the connection between these points, and this connection can demonstrate for us if it is a good connection or not good connection. So maybe it gives us more details for specifically the points that are interacted between them.
Why GNN?
Yeah,
why not convolutional network? Why not?
Yes, convolution. Yes. So it's a choice to begin with the GNN, but specifically for the CNN. So we need a specific data, and the data that I have that need to perform with the GNN model, because the data is specific data which is yellow files, and in these yellow files you have a yellow file, and this yellow file you have yellow file. In each file finally you have three type of data or files, which is the protein point PDB, the ligand point PDB, or the ligand point STF, and the pocket point PDB, which is include a summarize of these interactions between them. So to do this, we need a specific model that understands this type of data, which is the GNN model.
Once you run the model,
Yes.
you get the results. Did you check the accuracy of the results themselves?
So I have a problem in the processing of the data in this step, because it is large data that need further checkup for this data. But we are doing this. But I didn't have the result of accuracy to see if it's really have a good result before. Compared to
just to see the intent of your research topic.
yes.
So you know that for its research topic, we have an application of links to apply. So for your research, I see that it's very interesting. Which community of scientists you funded for this research? Pharma?
Yes.
Or just doors that for research?
Yes, thank you for your question. So we didn't publish it yet. We will be publish it very soon, this application. And to respond to your question, it's specifically for the research, but we have a discussion to more facilitate and do some tutorial and video to demonstrate for all the users that even a sample student that can be understand a small introduction of the docking and using it and see the results, because it will contain some tutorial and some specific courses about the docking, what this mean, and etc.
By the end, which will be, it's very YouTube, I know that, but
Yes.
what will be the utility of yours?
Yes, so if you are doing docking, there is multiple tools. Yes, but these tools are what is the difference between them. So if you open any tool, you have to upload the file of protein, wait for the process, the preparation of this protein, upload the ligands, and wait for the processing of these ligands, and then do the docking and enter your parameters. So it is very difficult. But if with my type, which is automating, which what I do specifically is doing a Python script to generate all of this by just you need to put, for example, 5GO, just the identifier number, and it will be run, and you have your results. So it's more easier.
So thank you very much, Mohammed, for this nice
Thank you.
work and this nice presentation. You just mentioned that you are intending to publish this work.
Yes.
For the other users to
Yes.
use this nice solution. So my question regarding the use of this solution. So will it be accessible for everyone?
Yes.
Or what will be the process?
So we didn't very discuss this, but I think yes, why not? We can do it for an open access as the other tools, and we can have also the database that we are creating, which is the oncoligand database. So we did the part of solid cancer, and we can continue with the liquid cancer. And why not? You can just enter your interface, and you have also the database that are prepared. So you have to just give the number of this data and perform your docking, and it will be much easier for everyone. Yes.
And how can you convince the research community to use this nice solution? Will you validate it somehow? Does it need validation and comparison with
Yes,
other
yes.
available, for
Yes.
example, tools? it would be nice to,
Yes.
to highlight the advantages of this.
Yes, thank you for your question. Actually, I did this part, but I didn't mention it here. Yes, we did a validation part. We compared this tool with other tools that are available, like Autodoc Vena and SimDoc Vena, which is utilize this, the same algorithm, which is Vena library. And actually, we had a great result in terms, specifically of execution time. So our tool is more rapid. Also, in terms of the affinity score, we have exactly the same. In sample case, we have maybe 0.1 or 0.2 minus. And for the visualization, we need to work more of visualization. But yes, in the figure, yes, it is the same. So thank you for your question.
Very nice. We're looking forward to the publication.
Very soon, inshallah.
Do you have any more questions?
Yes. Also, I would recommend to mention that this tool, it's an open, and we can add some other page to do with, for example, the molecular dynamic, which is also will be very soon published to add other, so which is the dynamic part. Because as we know, we have the GROMAX or the AMBER, but are a little bit difficult and need some command line, but I'd like to do it also automated, so you can just click after your docking, click and do also the dynamic moleculars. Thank you.
So now we have another presenter. Omnia, are you hearing us?
Yeah, I'm hearing you. So you can hear me? Hello? 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 You can hear me? Hello? 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 You can hear me now? Hello? Could I start now? Could I start now?
Okay, so I think that we have a problem with, so Omnia is not available, so she's not
You can
hearing
hear
us.
now?
We have the presentation, but Omnia is not with us. She is not connected. So maybe we can,
Hello?
do this presentation
Hello?
later on. But
Hello?
now we will have
Hello?
um, lunch break, and
Hello?
we need to be here
Hello?
at 3, because we will
Hello?
start our panel session with Professor Dr. Slim Abdelnader. So we we would like to have all the attendance here at
Hello?
3. Okay, mainly student. Okay, but we have panel session later on AI. Okay, thank you very much.
Hello? 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 Hello?